In this video, I'm going to talk about torque. It's part of option B from the old syllabus and part of topic A4 of the new syllabus for physics IB. In the new syllabus, it's only relevant for HL students. Please take a moment to read the success criteria I plan to cover in this video. So let's first talk about the difference between translational or linear motion and rotational motion. So in this example, this is what you'd normally see back in kinematics, is we would push on a box, and a lot of the time we would make the box so small that we really would ignore if I'm pushing in the middle or at the top or at the bottom. If I don't have a large enough base, you know if I push at the top, it's actually going to rotate. So in the other parts of the course, we kind of ignore that. Here with rotational motion, instead of talking about a force, we're going to talk about a torque, because there's a little bit more to it. If I try and change this spanner or this wrench and I'm pushing it here, I'm going to have a really difficult time. But if I go down to the end of the handle here, and I now apply the same force, but at a larger distance away from this pivot or this fulcrum here, then I'm actually going to have a much larger torque. I'm going to have a much better ability to rotate this wrench around. So that's why we say torque is a measure of the force that can cause an object to rotate about an axis. But it's not directly force, so it's not going to be measured in newtons. So let's look at the data booklet. And right now, we have last exams for 2024 on using this in option B, and first exams in May 25, and it looks like this. You'll see that the equations look very similar. Right here is our equation for torque, or right here. So in the old syllabus, we're using gamma, capital gamma, not the what I usually say, the dead fish. That's the lowercase gamma. And over here, we use the letter tau for torque. Notice they otherwise are exactly the same. So how am I going to calculate torque? Now, to be honest, in my class, I usually say ignore the sine theta because it all depends on where theta is measured from. What I usually say is that you need to have your force and your radius perpendicular to each other. And if they're not perpendicular, like I have in this diagram, then you need to take a component. Now we can do this in two different ways. In this case, for F, I could have one component of my force in this direction and the other in this direction. Notice this will not help me turn my wrench. The only part that's going to actually cause any rotation is this angle right here. Now, this angle, if I just draw it here, opposite over hypotenuse, that will be sine. So this side here will be F sine theta. It's usually easier to break the force down into its components, but you actually could think the same way with the radius. Now if I connected a line right here, instead of thinking about breaking F into components, I could break my distance into perpendicular to the force or parallel to the force. Now notice I do have a right angle triangle right here. And compared to theta, this again is opposite, and D would be the hypotenuse. So if I want to look at this dotted line here, this would be D sine theta. So in either way, to calculate the torque here, I am going to take my force that's perpendicular to my distance. So breaking down the force, I would have F sine theta times the distance, or I could say I'm going to have my full force, but I'm only going to move it over the distance D sine theta, the green dotted line. Either way is valid. So what does this mean in terms of equilibrium? Because most of our questions at this point will deal with equilibrium. Now, if this is in rotational equilibrium, then that means it's neither going to rotate clockwise or counterclockwise. In this case, the torque, because of mass 2, will try and make my beam here rotate clockwise, whereas mass 1 here would try and make it rotate counterclockwise, or you could also say anticlockwise. If this beam is not rotating, we will say it's in equilibrium. That means the torques that are going clockwise will have to equal the torque trying to make it spin counterclockwise. Now remember, we've already done translational or linear equilibrium. If we're just talking about moving in a straight line, translation or linear motion, then that means all the forces must be balanced. So let's do some examples. They really will help. The first part says, let's calculate the force the pivot applies to the beam. So here's the example just like I had in the last part, except for now I have some values. Part A says calculate the force the pivot applies to the beam. So since it's not rotating and it's not moving vertically or horizontally, I also know that the forces are balanced. In this case, let's think about the forces in the vertical direction. That means in the up direction will equal the down direction. Pushing up, this will be the normal force that's applied to the beam. And down, I have two forces of gravity, one from the 2 kilogram box and the other one from the 4 kilogram box. So if I pick up my calculator, I get a total of 58.8 newtons. I'll just write that up here for the next part of the question. Now in part B, we're asked to show that the torques are balanced about the pivot. So here's our point right here. And in this case, I'm going to have this force of gravity pulling it down clockwise, and this one trying to pull it down counterclockwise. In this case, clockwise, we will have a torque that will be our force at a certain radius. In this case, it's going to be its weight, so 4 times 9.8, and the radius here is 25 centimeters, so 0.25. And I pick up my calculator and my value is 9.8. Now for the counterclockwise direction, I have a weight of this 2 kilogram, so that will be 2 times 9.8, and its distance is 50 centimeters or 0.5 meters. Picking up my calculator, I get 9.8. Now, the thing about rotational equilibrium is it's not just about one point. If it's actually in equilibrium, I should be able to choose any point. In part C, I'm asked to use a point not here at this pivot, but rather right here. So let's look at what's going to cause torque about this point. Well, clockwise will still be the 4 kilogram mass trying to cause a force in this direction. So the torque will be the weight times the radius. In this case, the weight is still 4 times 9.8. And the radius in this case is going to be 75 centimeters from our pivot point, 0.75. Picking up my calculator, that gives me 29.4. Now let's look in the counterclockwise direction. In that case, this normal force is going to actually try and rotate it in a counterclockwise direction. So from before, we have that that's 58.8 newtons. And our distance here is 50 centimeters, 0.5 meters. And when I put that in my calculator, I get 29.4. And it's true that I don't have the same value as I did before, but they are still balanced. Let's just double check this for a second. What are the units? Well, if it's force times a radius, it's meters times newtons. Or a lot of the times we'll write meter newtons so that we don't get confused with any other units like, say, joules. So here's another example. I have a swing hanging from a tree branch, and we're going to just ignore the fact that it has two connections here, and we'll just pretend it's connected at one point. Describe why the swing is in translational and rotational equilibrium. All the forces are balanced, so it's in translational equilibrium. There is no acceleration in any direction. All the torques are balanced, so it's in rotational equilibrium. It is not rotating in any direction. So a child comes to sit on the swing for part B. Together the child and the swing have a mass of 45 kilograms. What is the torque applied to this branch? Notice that this is straight down, and I gave you the horizontal distance. Therefore, our force and our radius are already perpendicular to each other, so I don't need to worry about the sine theta part of my equation. The force is not 45 kilograms, it's 45 times 9.8. I need the weight, times the radius in my picture says 1.75. That's going to give me 771.75. This is going to be approximately 770 meter newtons. If this is the maximum torque that can be supplied to the branch before breaking, suggest how the swing could be adjusted for larger children. Well, somehow I'm going to have to have the similar torque or lower. Now we're going to assume that the larger children will have a larger weight and therefore a greater force pulling down. So the only way to compensate for a larger force would be to have a smaller radius. So what are we going to have to do? We need to move the swing closer to the tree. So here we are in example 3. We have a mass of 40 kilograms and the length is 2.4 meters. So we are going to assume its center of mass is going to be right here in the center. So this would be a radius then of 1.2 meters. We have our tension pulling up and it's supporting our beam. And it's asking for us to calculate this tension. Now remember, if we want to be able to do this, our radius and our forces have to be perpendicular to each other. So what we're really interested in here is this component of the tension. In this case, it will be tension sine 30. So since it's in equilibrium, we'll know that the torques counterclockwise will equal the torque clockwise. So clockwise, that will be the weight of the beam at its radius of 1.2 meters. Counterclockwise will be our torque, will be the torque caused by the tension. So that will be T sine 30 at its radius of 2.4. And when I put that in my calculator, I get 392 newtons. Part B, what are the vertical and horizontal forces that the wall exerts on the beam? Well, let's look at all the forces vertically. I'm going to have up will have to be the same as down. And upwards, I have T sine 30. And right here, there must be a part that's pushing up as well. So we're going to say that's the normal force from the wall. Let me just call that wall. And that's going to equal the weight of the beam down. My calculator gives me 196 newtons. Now if I do the same thing left and right, some of this tension is pulling to the left. That would be T cos 30. And to the right, that must be the wall pushing it back, not allowing the beam to continue. So I'm just going to call that wall. And in this case, my calculator gives me 340 newtons. So please take a moment and read the success criteria. After this video, I hope you can say yes to both of these points.